Hello guys, my name is Masemla Talang. I'm a tutor for Axis Academia. I'm a best tutor and a physics tutor. But today I'm going to render a lesson. The lesson is all about second geometry. So our objective today is simply the theorems. Then we'll also do a Dr. Kipton and apply it, showing how to apply it. Okay. So I'll start by the first. I won't say the first theorem, but then just name of the theorem. Where it's a line flows from center perpendicular to a chord. It bisects the chord. So one can ask or want to understand how this theorem works. And we have to know that the theorem, it can be defined or can be explained in three ways. You can say a line going from center perpendicular to a chord, it bisects the chord. Or you can simply say a line going from center to a midpoint of a chord is perpendicular to a chord. Because we know that the moment we say a line is to the midpoint, it means from AD to DB is equal. When it's equal, then we're going to bisect the chord. So whenever they give you a statement, they say it to a midpoint or it perpendicular to a chord, you must know that both sides of bisect the chord. The weight bisect and the weight perpendicular, they go hand in hand. And you must know that if you have given this diagram, then this line is like this: A, C, D. And they didn't say anything to you, or they didn't specify that this line is to the midpoint of the chord. You must not assume, because in second geometry you don't assume. Everything that you do, you must be told. I think I'm much clear on that. So I'll move on to the second theorem, which says an angle and a circumference is 2 times an angle at center is 2 times an angle at circumference. So the angle at center is determined, or it can be expressed in different ways. This shape is called what? It's called a concave kite. A concave kite is because we know that the kite is more like this. So now the last edge of the kite is on the center. Someone can ask, when does the angle at center applies? Angle at center applies when the 3 vertices of the concave kite are on the circumference. 1, 2, 3 are on the circumference, and 1 is at center. That's where we say an angle at center theorem applies. We say the angle at center is twice the angle at circumference, or you can say the angle at circumference is half the angle at center. Another way to describe it, or another way to find it or to identify it, you can say is the angles that are subtended by the same arc, which is this arc. This arc subtends this angle at center and subtends the angle at the angle at circumference. And you must always bear in mind that if the 3 vertices are not on the circumference and 1 is not at center, the angle at center does not apply. If you are given this diagram, you must take note that 3 vertices are at what? Are at the circumference, but this one is not at center. And never ever assume, if they didn't give you a center, never assume that this is a center, unless to the statement or that they've shown you that this is a center. Then you know that we have another way of angle at center, which is an equivalent. There are equilateral, which says this angle, which is 2x, this is x. We say the 3 vertices must be at what? At the circumference, while 1 is at what? While 1 is at center. Then we go again to say what? They are also subtended by the same arc. Subtend this angle and this angle. Another way we have what? We have a bow tie, which can be expressed this way and can also be expressed this way, where this is x, this is 2x, this is 2x, this is x. Again, you can see that the three vertices of this bow tie are at what? Are at the circumference, while one is at what? At center. They are also subtended by this arc. Even in this side, this arc subtend this angle and this angle. Three vertices at the circumference, one at what? One at center. Always, you must know it. Then another thing that you should be in mind of, they can produce another diagram more like this. This angle and this angle. The same axis here. Three vertices are at what? Are the circumference. 1, 2, 3. And one is at what? One is at center. And you must know that that's where the angle at center applies. If you can see, this diagram and this diagram are much similar. They just took this point and place it this side. Meaning that they can also take this point, put it here, then it's going to be like this. And this angle and this angle. That's what we call angle and center. Possible lesson. And now we're going to focus on Tanquet theorem. So Tanquet theorem is has a tangent and has a what? Has a triangle. Where we say the tangent, there's a triangle. Where we say this angle is equal to this angle, while this one equal to this one. Okay, someone can ask, how can I know which angles are equal? Okay, we are saying the angle that is between the chord and a tangent, which is what? Which is this angle, is equal to the angle on the alternate segment. In a simpler way, we can say the angle that is formed between a tangent and a chord, the very same angle that is opposite to the chord, is equal to the what? Is equal to the angle that was formed in between the tangent and the chord. Okay, let me repeat. The angle that is formed between a tangent and a chord is equal to the same angle that is opposite to the same chord that subtends the angle that is adjacent to the what? To the tangent, which is this angle. We are saying the angle is formed between the tangent and the chord. Then the same chord, the angle that is opposite to the chord, is this angle. Is equal to this angle that was formed. Another way you can see is that simplify. This is a mock-up. Then you simplify this as a what? As a tangent. We go with a chord. Then angle that is facing this head of a snake is what? Is the angle that is equal to the angle that was formed between a tangent and a chord. Okay. We can continue. I'll continue doing cyclic chord. Cyclic chord is an equilateral. That is what? That is inside a circle. Where we say the opposite angles, x plus y equals to 180. Meaning the two opposite angles in a cyclic chord are supplementary. They add up to 180. Okay, someone can ask, how can I identify a shape to classify if a shape is cyclic chord or not? A cyclic chord, I just said that is a quadrilateral that is inside the what? The circle, but it also has to touch the circumference of the what? Of the circle. Meaning all the four vertices must be on what? On the circumference, which is 1, 2, 3, 4. They are all on the circumference. Another way you can identify A cyclic quad is a bow tie that is within the what? That is within the circle, which you say the four vertices are also what? At the circumference. Then we know that this angle is equal to this angle, and this angle is equal to the same chord subtend this angle and this angle. The same chord subtend this angle and this angle. Even if it's not closed, this shape, we must know that it's a cyclic quad. Because if we close here, we know that this angle also be equal to this angle. Even if we use this chord, it's equal to subtend this angle here and this angle here. Meaning they're going to be equal. So we can conclude that this is what? This is a cyclic quad.